Hi everybody, just want to start by saying really well done on your inorganic test results. They were really brilliant. I was so pleased with them and I'm sure you all are too. So obviously we've finished a unit, we've done all the assessments, and in order for you to have work to do during the school closure, we're going to have to start the next wee bit, which involves starting the physical chemistry unit. Not ideal if I'm not in school, but I just thought I'd make this quick video to just explain the first part to you, and then hopefully you'll have plenty of work to do while the school is closed. So in the physical unit, we're going to look at chemical reactions basically, and we'll spend a bit of time looking at pH, so looking at acids and alkalis, how indicators work. We'll look at buffers. We'll look at reaction feasibility, so how feasible it is, so how likely it is that a chemical reaction will take place. And we will also look at kinetics of chemical reactions. But we're going to start by revisiting this idea of chemical equilibrium that was introduced to you at Higher. So we're thinking about a dynamic equilibrium, which is obviously an equilibrium position that will move. So just to highlight this idea of dynamic equilibrium and how equilibrium positions will move based on the conditions that they're under. So you were told and you learned that things like temperature, concentration, pressure will all affect the equilibrium position of various chemical reactions. So this little example here highlights that quite nicely. You may have seen it before. So we'll start with this frozen gas, which is a dimer. It's dinitrogen tetroxide. It's a kind of pale brown, yellowy colour. And if we bring that up to room temperature, this reaction starts to happen. So the dimer breaks down to give us nitrogen dioxide gas, which is a dark brown colour. So simply by warming it up, we see this change in colour. So when we see this change in colour, we know that there is a chemical reaction happening here. Now, as that reaction happens and we get a higher concentration of nitrogen dioxide, the reverse reaction starts to happen. So rather than just seeing an increasing concentration of this brown colour, we begin to see it lighten again as the reverse reaction happens, as these two nitrogen dioxide molecules form or reform the dimer. Now this will keep happening, and it will go back and forward as time moves on, until eventually equilibrium is achieved. And at this point, the colour so this is like a closed system, and the colour inside this bottle will remain constant. So it just is quite nice to highlight how equilibrium positions will shift and change, and therefore this colour shifts and change until it becomes constant, indicating to us that indeed the equilibrium position is also constant. So just from Higher, this is just a definition that you will be familiar with. A chemical reaction is an equilibrium when the composition of the reactants and products remains constant indefinitely. Now keeping in mind this is in a closed system. So just like in that picture in the last slide, the little jar, nothing can get in, there's no oxygen getting in, the temperature will remain constant, the concentration constant, the pressure constant. So in a closed system, the equilibrium position will remain constant indefinitely. So until now, the position of equilibrium has been described in terms of the rate at which reactants and products are formed. But now we're going to have a look at quantifying the equilibrium position, and we do this by looking at the concentrations of reactants when they are at equilibrium. So here is a little table. It's just that same system that we looked at, this dimer, dinitrogen tetroxide, forming the nitrogen dioxide gas there. So this is a table of initial and equilibrium concentrations of each of these gases. The initial concentrations are not very important. You don't need to really pay attention to them because what we are interested in is the concentrations at equilibrium, and they allow us to work out an equilibrium constant. Now the idea of an equilibrium constant was first proposed by these two guys. So everything you've done in higher and what we're looking at today was all thought about by these two guys here, and they proposed the law of chemical equilibrium and gave it the symbol K. K stands for the equilibrium constant. You may also see it in different literature written as K with a little subscript C, but it's just the same thing. I believe this is also in that front page of your data booklet. Okay, so just looking a general description of any reaction. Okay, you have your reactants here and you have your products. This little reversible arrow with the arrows the same size on both sides shows that the equilibrium is constant. So we have A representing our first reactant, B our second reactant, C our first product, and D our second product, just as an example. This is a balanced chemical reaction, and these little kind of lowercase a, b, c and d just represent the coefficients that we put in front of these reactants and products just to balance them up. So here is our equilibrium expression. To work out the equilibrium constant, which is K, you take the concentrations of each of the reactants and each of the products. So we start with the products on the top, C and D, and the concentration of each of the products is raised to the power of the coefficient that we use to balance it. So C would be raised to the power of C, D to D, and then we have our reactants in the bottom. Whenever we're just kind of highlighting that something is a concentration, we put it in these square brackets. So we're going to look at some examples of this now. Okay, so you could be asked to write the equilibrium expression for the following reaction. So we have two, this is an ozone molecule forming an oxygen molecule. Now, bearing in mind, you're being asked to write an equilibrium expression. That word's really important. It doesn't mean that there are any calculations involved in this. You're merely writing the expression. So the first thing you need to do is identify the product, which in this case is O2, and the reactant, in this case, is O3. We then use the number of moles given in the balanced equation as the powers. So we would write that as K equals our product. It has a 3 in front of it, so it's to the power 3 over the concentration of our reactant, which is O3 to the power 2. So this is the equilibrium expression. And sometimes if you have a look at past papers, that is all you're asked for. So when you're asked for the equilibrium expression, this is what you write. There is no calculation involved in this. Okay, so if we have a look at a different example, our product here is ammonia. So NH3 in square brackets to represent that we're talking about the concentration of ammonia. And our reactants are N2 and H2. And if we want to write the equilibrium expression, it is K equals our products, which is NH3. We look at our balanced equation, it'll be NH3 to the power of 2, and we divide that by the concentration of our reactant. So N2 has no coefficient in front, and H2 has a 3 in front. This is the equilibrium expression for the formation of ammonia. But what exactly does all this mean? So for any given reaction at any temperature, the equilibrium, so the ratio between the products and reactants will be constant no matter how much of each you have. Okay, so this value K will always be the same. So if you remember from higher that at equilibrium concentrations of your reactants and products are constant, not necessarily the same, but are constant, it sort of makes sense that this equilibrium constant, which is a value, a ratio of those concentration values, will also be constant. So if we have a wee look at actually working out what the equilibrium equilibrium constant is, here we have just that same reaction as before, the formation of ammonia. Initially you use 1 mole per litre of nitrogen and 1 of hydrogen, and you have 0 of ammonia because we're right at the very start. Now these values don't matter because all we're concentrating on is the concentration of these reactants and these products at equilibrium. So at equilibrium, these are the values that I have. I have 0.921 moles per litre, that just means moles per litre, of nitrogen, 0.763 of hydrogen, and 0.157 moles per litre of ammonia at equilibrium. And because we know the concentration values at equilibrium, we can then work out the equilibrium constant. So I would always start by writing the equilibrium expression, which in this case is our product, which is ammonia to the power 2 over the concentration of our reactants. We would then simply plug in the numbers. Okay, so our concentration of ammonia is 0.157 to the power of 2. Concentration of nitrogen is 0.921, and of hydrogen is 0.763 to the power 3. And when you plug that in your calculator, making sure that we're plugging it in our calculator correctly, we end up with a value of 0.0603, and that is the equilibrium constant for this reaction. And under these conditions, at this same temperature, that value will always be the same. In terms of units, there are no units, so you don't need to remember them. Although we're using moles per litre as our units of concentration, this is a constant, so it's unitless. Okay, so please remember this. K as a value for a reaction is the same no matter what the initial concentrations are. The equilibrium will always go to this ratio and therefore have the same K value for any particular reaction. So let's look at a couple of examples where you might be asked to work out or use this value to work out an unknown. So you can fill this in your notes as we go through it. What is the equilibrium constant for the reaction stated here? At equilibrium, those are your concentrations. So I would always start by writing out my equilibrium expression. Okay, so if you just fill this in as you go. So there's my expression. I can now just plug in these values. So I've plugged in those values. I then just need to put that into my calculator and I'll work that out and I get an answer of 1.14 times 10 to the negative 5. And this value is K for this reaction. So that's one example of the type of calculation that you might be asked to complete in terms of equilibrium constants. Another example is where you may this time be given the value of K and be asked to work that back and calculate the concentration of either one of your reactants or indeed your products. I'll just point out a wee mistake here. I've put two different temperatures. They should both be the same temperature. So this time you're calculating the equilibrium concentration of PCl5 at 300 Kelvin, which is something we'll look at in more detail when we look at reaction feasibility, when equilibrium concentrations of PCl3 and Cl2 are both 0.5 moles per litre. So again, just start by writing out your equilibrium constant. There's no coefficients balancing this, so we don't need to bother with any powers. So we'll just plug it in. K is 9.6. Concentration of both our reactants is 0.5. Over PCl5. That is what we are trying to work out. So if we just rearrange that accordingly, we've got 0.5 and our next concentration of 0.5 over 9.6, if you can all see how that was rearranged. We then just plug that into the calculator and we get a value of 0.026. Now remember, the difference in this example is that we are actually working out a concentration, so we need to add in the units of moles per litre. Okay, so what exactly does this value of K mean? We don't just work out the value of K for no reason, just to give us a number and just to give us a calculation to do. It actually tells us and gives us a lot of information about how a reaction happens. Okay, so we're going to look at what it means when the value of K is small and what it means when the value of K is large. So generally, when we have a large K value, the position of equilibrium lies well to the product side, so lies well to the right. And we have a small K value, it lies to the left, so to the reactant side. And on that second booklet that you have, there's like 4 pages of questions, but on that very first page there's a nice wee table that highlights all this for you. Okay, so let's have a wee look at when K is small. So we have this reaction here, and we have nitrogen reacting with oxygen to give us nitrogen dioxide. Okay, K is small. It's 1 times 10 to the negative 30, so that's obviously a very small number. And when K is small, it indicates to us that we have a much higher concentration of reactants than we do of products. So if we have a little think about this in terms of an equilibrium expression, if I just write that out, you can write this into your notes as well if you want. There is our equilibrium expression. And if we were thinking about this in terms of a fraction, this here would have the higher value because it has the higher concentrations. And when we have small over large, it will inevitably give us a very small number. So when we have a small K value, we will always favour the reactant side and we'll have a higher concentration of reactants, meaning that the equilibrium position will lie well over to the left-hand side. On the other hand, when we have a large K value, like we have here, 2 times 10 to the 22, which is a huge number, it tends to tell us that the equilibrium position lies to the right, so lies to the product side, which means we have a higher concentration of our products. The equilibrium expression for this would be as follows. Again, please write anything you want down into your own notes for reference. So this time we have our large number on the top. And when we have large over small in terms of a fraction, that will always give us a large value. And in this case, the equilibrium position will lie well to the right. Now this is what we're looking for in all chemical reactions. The whole point of a chemical reaction is to obtain a product. So it is always favourable to have our equilibrium position lying to the right and a larger K value. You will also get see some examples where K just lies in the middle, and we have a kind of in the middle sort of value, anything from like 0 and in single digits. That means that our concentrations are more or less equal. If you have, just refer to that table that I said, I pointed out in your question booklet there. When you're asked about the position of K, you will really only be asked about a K value that is either really small or really large. So I don't want you to get too worried about arbitrary cut-off points about when the value of K is this, it means it's low. When it's in the middle, this is the value range. When it's high and such. So when you're asked a question about this, it will be very obvious what your K value is, whether it's low or whether it's high. Another important thing to note, we're nearly finished, you'll be glad to know. Is that temperature is the only thing that affects the value of K. Pressure, concentration will not affect the equilibrium constant. So for endothermic reactions, a rise in temperature causes an increase in K, and that is obviously what we are looking for in terms of a chemical reaction. And for exothermic reactions, a rise in temperature will cause a decrease in the equilibrium constant. So just remember, changing concentrations, changing pressure, and also using a catalyst will not affect the value of K. One more little thing to point out. When we're talking about equilibrium constants, we only really take into consideration or we don't even take into consideration the concentrations of pure solids. So if you look at this, anything that has like an S or an L state symbol, they just have a value of 1. Okay, so we would not include them in our equilibrium expression. Now, I realise that was quite a lot, especially sitting there watching a video to take in. I will post the link to this on the Teams page, so keep referring back to it in bits and watching over bits as you see fit. Please also just send me a wee email if you want anything, if you want me to go over anything. But here's that table I was talking about. You have 4 pages of questions based on everything that we've just done. That should be plenty for you to be getting on with when the school is closed. I would also kind of point you in the direction of Scholar. I'm sure you'll have logins. If you don't have a login, you can send me an email and I'll sort it out. Also, Miss Adams' YouTube page is really good for this bit as well. It's actually really good for everything. But anything I can do to help, send me a wee email and I'll see you in the new building.